Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are moving to the practice question of the atomic physics. As you all know that we completed the atomic physics chapter, and this is the practice questions for the last part of that unit. And then we move on to the diploma questions. Then we officially end this chapter. So let's do some practice questions of starting with the mass defect. The question says if the nuclear mass defect of an isotope is 0.095298 U, determine the binding energy in MeV. Basically, the binding energy means we have to find the energy. So the energy we then find from the Einstein equation. So where E is equal to delta M C square. We have the mass defect, but we want this in kgs. This is in U. So 0.095298 U, you have to convert this by multiplying 1 by 1.6 10 raised to minus 27 kgs divided by 1 U. So U and U cancel. Your mass defect in kgs is this. And you have to take this mass over there, this defect mass, into 10 raised to minus 20 kgs. And your C scale is 3.00 10 raised to power 8 meter per second square. When you calculate this, you get about 1.4237 into 10 raised to power minus 11 joules. But you want this in MeV. So first we convert this into EV by dividing by 1.6 to 10 raised to minus 19 coulombs. Then divide this by 10 raised to power 6 EV, which is 1 ME. So EV and EV cancel out, and we have joules and joules cancel out. This is basically the joules. So when you solve this whole thing, you get the answer in MeV, which is 88.985 MeV. So this is a binding energy of an isotope. That's how you can deal with question. Make sure you have to convert this first when you use in this Einstein equation. We have the next one. This is some of the theoretical based question. You have to know some theory about the alpha decay, beta decay, and gamma decay to these type of questions. So what's the theory on this? So we have to match the particles to their respective threads. That which thread they follow, the particles. Or the source of alpha, beta negative, beta positive, and gamma radiations pass through a magnetic field directly into the page as shown. So this is a type of the thing, and we have to say that which is like A, but I'll find for A. So basically, you can see over there that source is over there, magnetic field goes downwards. That A goes downwards at this B point. Basically, at this B point, the straight B point, this stays the neutral. In that thing, this stays the neutral thing. You have to know in this. This is the neutral thing. The negative thing is always down. So there's a negative thing over there, and this is a positive thing. So the A. If the A is like a negative thing, if the A become a negative, so you go down. So they go towards the negative thing. So which means the A should be bigger negative. And for B, B goes up thing. Okay, B does the neutral thing, which has the no effect of this. So B you have to get your gamma thing. B is your gamma. Then C goes over there. It's not goes over like a bottom or the top of thing. It goes like the straight thing near the B. When it goes like straight thing near the B, like they do their own path. This is called the alpha decay. And the last thing we're left with, which is the beta positive, because it goes upwards. If this thing is your negative, so this is positive, and this goes beta positive. So which means the beta positive we have. The theoretical based question, you have to know something about this thing. Next thing, we have to make complete a balanced nuclear equations. We have to write that. So for each of the following decay directions, firstly we have alpha decay of the American 343, which is AM 243. So firstly we have to know this format, that rule of that how can we make this. So we have AM, which is 243, and you can check from your periodic table that which number they have. So this has 95. This will make the alpha 42, and this will make the another thing which will do 243 minus 4, which you get 239, And then 95 minus 2, you get 93. And 93 number, you have NP. This is all something now. You can see from your periodic table. So that's how you can make the nuclear equations. Alpha decay of the parent isotope to produce a daughter nucleus of the thorium 231. They sometimes confused you like this. So they give you that the thorium 235 can be made from there. So the thorium 231, which has the number of 90, and this is alpha decay, so it's 4 and 2. Now you do the backwards, so 231 plus 4 will give you 235. 90 plus 2 will get 92, and this is the uranium. There's a backward reaction we did. Next, we have a lead 1212, which is Pb212, decays to the bismuth 212 while the beta negative decay. So we have a beta negative decay now. So we do the same thing. We have Pb212, and this is number as 82. We do this reaction, we do the beta negative, so it's -1 and 0. This will produce the Bi, which remains to 1, but we have to plus 1 in this because this is a negative, so we have to plus. So 82 plus 1 is 83, and the anti-neutrino. So the products, like in this product is mainly there, and these products is mainly there in beta negative. Beta positive, we have another products. Dash should be there to show that thing. You not have to step that. That thing you have to make by your own. Sometimes they're given us like this, and sometimes you have to make. So we have a next question of this. So barium-9 is bombarded by the high-speed proton. If the daughter nucleus is barium-8, determine the another particle emitted. So basically, we have a high-speed proton, and this will make something. So Be9, which has the number of 4, bombarded with the proton. So we have a proton is involving in the reactant side, which is 1 will make a Be8, which that number stays the same because this has then some other isotopes. And the other thing is also made as the product. So we don't know that thing, so we take it as XAZ. We have to find the A and the Z. So you know that thing, that number of nucleons and number of the both side, the up thing and down thing is should be same. So for the A, if you want, so we do 9 plus 1, and this is equal to the 8 and plus A. So we have to find the A now. So when you find this, when you calculate this out, when you get about the 2. So you get this thing is 2. Another thing, we have to find the Z, which is again the same thing. 4 plus 1 is equal to 4. When you find this, you get a 1. So over there. So what is that thing? This is the hydrogen. This is another type of the hydrogen. So we can say that this is the hydrogen 2. Like we have 3 things. We have a 1, we have a 3, and this is 2. Then we have another. We have some isotopes of the hydrogen. That one is that isotope of the hydrogen, which is hydrogen 2. You can name it and like this. If you know the original name of this, you can write that too. So that's how you can find. You have to know that properties, that number of all the things from the reactants and the products should be same in the A or C. So that's what you have to do. Another question we have. The question says a 920 gram sample of the cobalt 60 has decayed to a final sample of 14.375 grams. If the half-life of the cobalt 60 is 5.3 years, tell me the time the sample was in storage. So we have to find the time. The what time? Okay, we have to find the time, which is the T. Not a T half, because they've given us the T half. They've given us the half-life time. We have to find a T, that thing. So basically, this is the half-life quotient. We have to know that this is the formula for that. This raised to power n, but we don't have directly the n given to us. So we take a T divided by the half. So you know that your small n is equal to T divided by T half. That you know. You have to isolate the things in this because you have something which you don't know in this for now. So you isolate this half thing. It stays over there like this, and that NO goes over there and they divide over there like this. You have N, you have NO, this is your N, and your NO is this. This is the initial thing I given to you. So you can keep doing with that thing, and you have 14.375 grams divided by 920 grams. Done. When you calculate this, you get about T upon T half is equal to, you get about 0.015625. Okay, we are over there. Now you know about the logarithms now. What are the logarithms? Logarithms are something when you like change the exponential form into logarithms. How can you change this? I will tell you that. So we have this over there. We have 0.015625 is equal to half, and we have half this. T half we have given, which is 5.3 years. So this is over there. Now you can change it to the logarithm form. How? So you can multiply both the things with the log. First you do this type. You do the logs on both sides. You can say that this too. T divided by 5.3 is like this. Now you do this. So this thing, if there's anything is like exponential to the another thing of the log function, this thing goes at the front of that log function. So the log of 0.015625 is equal to the t upon 5.3. You have a log half left with you. This is multiplying with that. After that, your log 0.015625 is divided by the log of the half. And that 5.3 goes over there with the multiplication. So it multiplies with that thing is equal to the t, which you have to find. So you set up all things. When you calculate this, you have to do the log thing in your calculator. You get about 31.8 years, which is basically the 32 years. So that's how you can find this. So that log thing on both sides is very important when you do like this type of question. When you do the approach to the logs, your logs are very easy to calculate, so you can do that approach too. So that's the answer for the this. In the activity half-life, you have to use the logs more. When you find the n, you have to find the t. You have to use that. Now you have some fission question, which is like a long calculation base. Uranium-235 mass is given, is bombarded with a slow-moving neutron, which is neutron's mass is given. As a result, at zone 141, the mass is given. Strontium-94 mass is again given. Are formed 2 neutrons are emitted. Determine the energy liberated in joules in this reaction and give you answers in 3 significant digits. So the long base question. So what are the reactants? So reactant, firstly we have a uranium-235, 92. Then we have a neutron, which has the 1 and 0. Then as a product, as a result, we get a xenon 140, which has 54. We have a strontium, which is 94, 38. And we have a 2 neutrons at the end are emitted. So these lots of things we have to find the energy. So basically we have to find the defect mass. So for this type of question, you have to do the mass of reactants minus the mass of the products, and all the masses you are given with you. So in the reactant side, we have a uranium. Uranium's mass is 235.044 U plus then we have a neutron, so 1.009 U minus this with their zone mass, which is 139.922 U plus 93.915 U plus 2 times 1009 U, which are the 2 neutrons. When you calculate this, you get about 0.198 U. You have to convert this into kgs, so multiply this by 1.66 into 10 raised to a minus 27 kgs. Divided by 1 U, U and U cancel out. You get your defect mass about 3.2868 into 10 raised to power minus 28 kgs. Defect mass is calculated in kgs. You have to do, so this is in kgs, and now put it in the energy formula, which is Einstein equation. So energy is 3.0 10 raised to power 8 meter per second scale. When you calculate this, you get about 2.96 into 10 raised to power minus 11 joules. They ask about you be in joules, so you have to be in joules. They're doing the lot of work we're doing, so they can't do like do the another equation after MEV. So we left over in the joules. So that's the type of question you get from the fission and fusion. Short questions, long questions, you get the both type of questions in that type of thing. Move on to the next question. We have to converting the masses. So the question says convert the following masses. First we have this and then we have this. Okay. We have to convert the 10 ME C square Krog into the kgs. So basically we have to go to the EV part first, then we move on to the joules after we do something else. Okay, we have to do this the mass into the joules first, into the joules something something. So first we have to divide this to go to the EV part, due to the EV part, that ME over there cancel out. Then from EV to joules, we have to again multiply this, because when we doing the backwards, we do all thing divide. Now we have to all thing multiply with this. Now your EV cancel out. From that you get your mass of about 1.6 into 10 raised to minus 12 joules per c square. Now joules per c square means that 1.6 10 raised to minus 12 joules divided by the 3.00 into 10 raised to power 8 meter per second scale. From here you can get your mass of 1.8 into 10 raised to power minus 29 kgs. That type of conversion you have to do when you do these type of questions. Done. And for the next one, to B part I do over there, that you have from mass of an alpha particle to GeVc square. Okay, first we have to find the energy. So what is the mass of the alpha particle? You have 6.65 10 raised to minus 27 kgs multiplied by 3.00 10 raised to power 8 meter per second square. When you find it out, you get about 5.985 into 10 raised to minus 10 joules in GeV. So first we continue to EV with the multiplication of that thing. And in GeV, so 1 GeV, divide this by 10 raised to power 9 EV. So EV cancel. You get about 3.74 GeV. Yeah, GeV. And C square you can write. And further on we can solve for GC square. But you left over there, then that's your answer for that. So that's all you can do with. This is A part and this is your B part of it. That's all we have to work in this. Now we have the last example, the last practical question of this thing and from the Quarks thing, which is very important. So determine the overall charge of the following combinations of the Quarks and the anti-Quarks. They give you the S and they use the D2 thing. So you have the table over there, so you can do from here. So for the A part, you have SDD. SDD means you have the S over there and which has the minus over there, which has the minus 1 by 3e. So minus 1 by 3e plus d and d, which is minus 1 by 3e, that you all know. That's from your first thing right over there. That's the same thing, and when you calculate this, you get about q of out minus electron, which is the 1 electron, minus 1. Then you have a USS, so U is 2 by 3e, right over there is plus, and then we have a S over there, which is minus 1 by 3e. So plus minus 1 by 3e plus minus 1 by 3e, and we get q of about now 0. The charge is 0 now. Then we have a UDD, that thing which is over there shows that this is the anti thing, which is the anti-clot, you can say. So this is the anti thing. So firstly for U, you can take 2 by 3e, and for the D, basically your D is over there is in minus 1 by 3, but there is an anti thing is the little bar on that, so we take it as a plus 1 by 3e. So that's just the thing you have to know in this. If there's an anti thing over there, this means the anti-clot. So if there's plus, you get here minus. If there's minus, you get here as a plus. And you get a E of about Q of about electron, which is 1 electron, positive electron. So that's how you can find the overall charge of that. That's all you have to do. So that's all for this part practice questions. We completed that part and we completed the practice question of course we have. So that's all for this lesson. Next class we do diploma questions and we completed that unit. So learn with very vibe, learn smart not harder. Please like and subscribe to my channel. If you have any questions, let me know in the comment section. See you in the next lesson. Till let's get it with Edu Vibe.